This word is pronounced chi. Do not say chai, do not say chi. Do not say any of those other things that you might want to say. It is called chi squared. And you know what's gonna happen is because I said that, people are just gonna call it chi squared just to irritate me under my skin. But that's fine as long as you know it's actually called chi squared. Yeah. It's not a T. What's chi? What is that? What is that actually? That I don't know. It's definitely a Greek letter chi. Okay. Um, if you did AP Bio, you have an introduction to chi-square already. Oh, it's really okay. I'm gonna pretend like you've never seen it before. So, but the the do step should be familiar to those of you who took AP Bio. Okay, guys. Shh. Okay. Chi-squared test of goodness of fit. There are some really good things about this chapter. It's simple. And I'll explain the advantages of this as we go. But chi-square test for goodness of fit is a test for comparing more than two proportions to a hypothetical claim. Okay, so think of it like a 3 sample proportion test, 4 sample proportion test, 5 sample proportion tests, 27 sample proportion test. Whenever it gets above 2 sample proportion test, then it knocks it into chi-square lengths. And that's because you can do one test for all of those things, which is great. One procedure. Okay. There's very important things here. Data must be categorical. And there must be, this is the most important thing for this, there must be a list that has counts in it, categorical counts of things. And I'm going to put a note there. This is some foreshadowing. They give you something that looks like it could be typed into L1. And this is how you're going to differentiate between the other chi-square things. Here's one piece of good news I'll give you now. There's no chi-square intervals. They're just tests. You don't have to memorize 2 different things to do. They're all tests. They're all the same, which is great. There's another really cool thing about it that I will explain after we draw a couple pictures. Okay. The state for this whole chapter has the ho, the ha, and alpha, and they're all just sentences. I know. Okay. And the reason it's sentences is because if you have a lot of proportions, you're not going to say like P1 equals 5 or 0.5, P2 equals, and you could. I think in the book, sometimes it does that. It does a list of the like population proportions, the claims. I thought you weren't coming. You're here. But that's good news. Okay, so there's a couple of things here. These are sentences. These should make sense. Okay, because there's so many proportions and so many different samples, we're too lazy to list them all out. So we just say a really, really vague sentence that covers everything. We just say, oh, the whole distribution is same as the claim. Here is where you're going to say what is in the problem, like cars or days of the week that are end in Y. Wait, that would not be that interesting because I think that's 100%. Days of the week that are above 80 degrees. So, whatever. Okay, now knowing what you know about the ho and the ha, what do you think the ha is in this case? There's a 2-word difference from the ho. Okay, different. It's actually a 3-word difference. Is different from. So you're just gonna say the same, and then you're gonna say it's different. That's it. The rule for alpha is the same as all of your other tests. If they give it to you, use it. If they don't, 0.05. Okay, now I'm going to add a note over here that says, or if they give you some other kind of wording that's not exactly this, just you can use the wording from the problem also. You could also do a list of all of the proportions if you wanted to, but I'm too lazy to do that. I might have done it some in the homework. I don't know. So there's actually 3 different ho and ha options, which is kind of annoying, but I'm going to go with this pretty much every time out of laziness. Okay, anyway, the plant. Okay, so Kai looks like a big fancy X with like a swoopy on the front, and he's tall. He's not like a lowercase guy. He's a tall guy. Here's how he looks on your formula sheets. Fancy. Okay, so it's called a chi-square test of goodness of fit. Okay, and I want you to think about that being like, how well do my samples fit the claim? And then you can be really, really bad grammar and say, how good do my samples fit the claim? Just to match it to goodness of fit. Okay, guess what? This is going to be crazy, but there's 3 conditions. Do I need to say anything after this? There's no difference here. It's random sample, random assignment. There should be some kind of randomness stated. If it's random assignment, 10% does not apply. I think we've got that down. I don't think I need to spend the time there, but the large counts condition is different. It's very easy. But different. And that is all expected counts are greater than or equal to 5. You guys are like, I don't know what expected counts are. So let's define that in this business. Unless maybe you took AP Bio, you know what expected counts are. No? Okay, so you have to do some math in the plan step, and you're gonna feel like you're wasting your time because it's the plan step, and you're like, why can't I just say CLT or something like that? But it's not a big deal. It's not a waste of time because you need your expected counts for your do step anyway. So you're just going to be doing some of the math up here that you're going to apply to your do step. I promise you it's not a waste of time. It's not like there's no dot plots here, there's no box plots, there's none of that. You're just going to do some multiplication. Okay, I'm gonna scooch this down, but I'm gonna leave this for a minute because we're gonna draw a picture here. So I can show you the other good news about chi-squared. Okay, there's only one thing for this chapter, the whole chapter on your yellow sheets. And it's right here at the bottom of the front page. You don't even need to label it. Don't get it out. It's fine. We're just going to use mine. It's chi-square equals, does anybody know what this is? What is this? It's capital sigma, which is the sum, observed minus expected squared over expected. So that's where you're going to use that math that you did in the plan step to plug those numbers in there. So chi-square equals the sum of observed minus expected squared over expected. And then I don't know if you guys noticed, but there's a chi-square CDF in your calculator. And the number that you get here is your low. Infinity is your high. And then degrees of freedom. Degrees of freedom is a little different for this. It's categories minus 1. And by categories, I mean how many different proportions are in the claim. This will make more sense once we start to do this M&M's problem that I'm hoping that you saw in your arts and crafts pages. Okay, I'm going to show you a picture from the internet, but we're not going to draw this particular picture. I just want you to see it. Oh, here it is. Okay, these are different chi-square graphs according to their degrees of freedom. We're going to draw a very simple one of these, and I'm going to explain where the shape, center, and spread come from and all of that. But notice the 1 degree of freedom and the 2 degrees of freedom, they kind of look like exponential decay. And then these are the usual, so they're always right skewed, which is why you get to put the chi-squared as your low every time. There's no tail on this side. There's not ever gonna be a negative infinity on these. So you don't have to memorize any of that. It's just chi-square, infinity, degrees of freedom every time, which is really great. That's one of the other things that make these really simple. But I do want you to notice that the picture improves as the degrees of freedom increase. What does it start to look more like? Like a normal curve. So as the degrees of freedom increase, it approaches normal. Do you care about that? Not really, because you're just going to go through the motions. But you know me, I can't leave all the stones unturned. I have to tell you all the things. So we're going to draw a very, very kind of crude one of these on here. So go ahead and draw in like degrees of freedom 1. That's bad. We wouldn't really use that. But before we do the other ones, we're going to talk about the shape and the center and spread. So we're going to do a description of the chi-square distribution. So the center, there's 2 centers. The mean of these graphs is the degrees of freedom. The mean is the degrees of freedom. That's easy. That's good. The mode, though, and the reason that you want the mode, we never want the mode, but the reason you want the mode is because if you're going to sketch it, you want to know where that peak is degrees of freedom minus 2. However, this only works if the degrees of freedom is greater than 2. You can't have a negative mode on these. So I'm making up this word. Exponential-ish. That's not what it is. I don't know what it is, but that's what it looks like to me as a math teacher. So I'm not going to ask you to describe one that looks like that. We would never. Why would you do this? You would just do a 2-sample proportion test. Like that wouldn't be something we would ever do. But anyway. This is the one you care about because that's all the ones we're going to do are always going to be right skewed, which is great, as I was saying. Okay, so we're going to do 2 little graphs. We're going to do a degrees of freedom of 4 and a degrees of freedom of 8. And we're going to sketch those on our picture. I'm going to do degrees of freedom of 4. I'll do that in pink. Okay, so degrees of freedom of 4. The mean is 4. And the mode is 2. Does that make sense? Okay, so mean equals 4. Mode equals 4 minus 2 equals 2. Okay, so what you're going to do is you're going to go to 2 on your graph, and it doesn't matter where because we're just doing a very loose sketch here. Just put a dot somewhere. And then that is a very typical looking chi-square. Okay, now I'm going to do one in green for 8. Oh, by the way, real quick, does it make sense that the mean is 4 and the mode is 2 if it's skewed? You guys remember this from chapter 2? What happens when a graph is skewed to the mean? Pulled into the tail. Pulled into the tail is what I'm looking for. And the reason I'm asking is because I just did the AP exam for 2025, and that was like part of the first question. Okay. Okay, so go to 6 and make it shorter this time because remember it approaches normal, it gets better as it goes. So make it look a little bit more symmetric-y. Okay, right after this is going to be the M&M's problem. So wherever you are in your notebook, put the M&M's problem in next. I'm gonna go on the back side. You guys are to satisfied.
There's gonna be a bunch of, back tables and flashlight tables and stuff. There'll be a big piece too. But it's not real money. No, you went to a rack, but you don't have a window.
I gamble all the time. That's terrible. And I know all the probabilities. I shouldn't do it.
They use stats teacher.
I know.
It was the last thing.
I know, but it's just so very fun.
Yeah, is she like,
No, I can't count cards. Well, I can, but you shouldn't. It's morally I mean, roughly. I don't look at it like that. Okay, guys. This is my fault. I've derailed us into talking about gambling. Okay. While you're setting this up, I'm gonna read the problem. M&M's produced at the Cleveland factory have the following distribution of colors: 20% blue, 20% orange, 20% green, 20% yellow, 10% red, 10% brown, which I believe is different from the claim I found on the internet, but that's okay, because it's a contrived math problem. Joey bought a large bag and found 14 blue, 9 orange, 5 green, 5 red, and 8 brown. State appropriate hypotheses for testing the company's claim about the color distribution in Joey's bag. Okay, you could, if you wanted to, you could go P blue equals 0.2, P orange equals 0.2, P green equals 0.2. Do you understand what I'm saying? If you wanted to list your hoe like that, you could. I'm not gonna do that. I'm too lazy. I'm gonna write a sentence that covers the whole thing. I'm going to say the distribution of M&M's colors in Joey's bag is the same as the claimed distribution. I don't know, might be less writing to list them. I'm not sure. Either way. Okay, what's the ha going to be? It was different from, yeah. No, I can't write M&Ms apparently. It's just too hard for me this morning. Oh, there is a typo. There's a typo. It's fine. In my printout. There's no yellow ones. I forgot to put the yellow ones on. Just add comma 14 yellow up there. Whoopsie. And I have this from last year. I didn't fix it though. What the heck? Yeah. Mr. Tava, you're usually pretty good, but I must have been burned out by this point. I don't know. But today I will fix it for next year. Anyway, okay. All right. Calculate the, oh, I should say the alpha level, even though it didn't ask me to. You guys can see where this is going. I literally just said state the hypotheses, but I can't trick you guys. You guys know that I'm just putting the 4 parts of the test in here. Calculate the expected counts and confirm they meet the large counts condition. Okay, this is your first time of doing the expected. And the first thing we need to do when we find the expected counts is we need to figure out the total M&Ms that he has, which it would have been impossible had you not known there was 14 yellow. Are you okay with me saying that there's 65 total M&Ms without us adding it all up? Okay. I'm going to put a whopping equals 65 up there. Okay, so for expected counts, this is new for you. What you do is you say, for the blue ones, there's 65 total, and the claimed proportion is 0.2, which is 13. So if the claim is true, there you should expect to have 13 of them in your sample of 65. Does that make sense? Okay, so now we're just going to keep going. Orange, green. His green was kind of on, but his orange was kind of off. Yellow. Red. And these can be decimals. Do not freak out about that, even though you're like, that's weird, but this is theoretical. And all of those need to be greater than or equal to 5 for it to be close enough to the chi-square shape that you get to use those probabilities. Any questions about how I got expected counts? Just make sure to use the same number. The biggest mistake that students make in this is they use the numbers from the sample times the claimed proportion, which is not going to get you anything. You're looking to see how different these numbers are from the ones that he actually has in his bag. Okay. Are you guys okay with this? Okay, now we're going to do the do step. Let me give you a second to write that down. Okay. This is going to be irritating. And it's only going to be irritating today. I'm going to make you do this by hand today. And then on Monday, I'm going to teach you how to do this on the calculator that's not so irritating. But today we have to do it by hand once so you can actually see the math. And you guys have to tell me if you had to do it by hand in AP Bio. I'm curious. Okay, so chi-squared equals. Okay, so the only thing I have is this formula. This is saying add up all of the observed minus expected squared over expected. Okay, we're going to start with blue. The observed blue was 14 in the bag. Observed means real, like from your sample. And the expected was 13. So 14 minus 13 squared over 13. That is called the blue term. The chi-squared term for that category, which is blue. Everybody good? And you're starting to see how irritating this is going to be, I think. So the orange is 9 minus 13 squared over 13. Green is 15 minus 13 squared over 13. And why do you think that we square them? Why is it chi-square? Where's your curiosity? Find that. Why are we're just copying down these horrible fractions from Mrs. Talbot's screen, but why is it chi-square? What about statistics? What happens when you square these ones down here? No, this one. What happens when you square this one or this one? Makes it positive. Yeah, we like to work with positives in statistics. So chi-square is literally just making them positive. Are you guys okay with me using last year's number from this? Do you know you could type this in on one fell swoop, but it's 2.385, which is not an unusual test statistic for you guys. That would be like a very usual z-score or t-score, something like that. Okay, we are going to look in the calculator at chi-square CDF. And see if you can find him. He's next to TCDF and inverse T, and all of their friends are all in the same menu. And because it's right skewed, we don't have to worry about any negatives, also because it's chi-square. So 2.385 is the low. Infinity is the high. And then degrees of freedom is categories minus one. 1, 2, 3, 4, 5, 6 categories. So degrees of freedom is 5. That's a that's a that's a very high p-value. That is a p-value I have to tell you, if I was taking the test, that would make me question my work. But does that really mean anything? No, it just means that you don't have any evidence that he's got a wonky sample. His sample looks pretty good. Okay, however, did you notice the gap in lines here? What does that say? Yeah, okay. The interpretation of this is exactly the same as all the others. What? I thought it was 16. No, we're so close. Okay, so assuming the hoe is true, but that's a really, really long way to say the hoe is true. Too bad you can't just say assuming the hoe is true. Dang it. Okay, now pause here. This is a little bit different from all the rest of them. This is the only thing that's different. Usually we would say sample mean or sample proportion. This would be like a million sample proportions. We would not say that. What we say is chi-square of 2.385 or more. And here's another cool thing. They're always or more because it's right skewed. I needed one more line there. School trying to cut my, I have 5 more minutes for the conclusion, but I can do it in 2 so you can get your phones. Okay. We really, really failed that time. I don't even know why we would do a test really, because his sample is just like almost exactly like the claim. And you can kind of tell from when you're doing the differences of the numbers. Okay, so two things before we go. First, on Monday, we're doing this again, but I'm gonna teach you how to do all of this stuff in L1, L2, which is going to make your life easier. And when we do that, the College Board only requires you to write the first two and the last one of the chi-square statistics. So you get to shorten that part as well. The last thing is that I have an excellent joke that I have to show you. I can come back to this screen in 2 seconds. But you must see my joke. It's really, really good. I'm really super excited about it. Do you like it? Tell me you like it.
Are you taking gym test today?
I can, yeah.